Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. We're continuing on the second part of the second topic, Recursion and Induction. This part is entitled Ordinal Recursion and Induction. And I am, once again, Bill Farmer. So ordinal recursion is based on a well order. So let's say we have a well order. S and less than. And then we can define a function, f, that takes an input, returns an output. We can define this function by ordinal recursion on this well order as follows. So the definition of f has this form. So we apply f to x, and then it's going to equal some expression. Now, e here just represents an expression. This expression could be very complicated, very big, and in that expression we could have some recursive calls to f. So this big expression can involve calls to f, and these are the arguments to f. And what we do is we assign every input a complexity. A complexity Ci, and that complexity will be a member of S. Now remember, S is a well order. That means that if we look at values if we pick out values in S and we keep picking smaller values, we'll eventually have to stop that process after a finite number of steps. In other words, there are no infinite descending sequences in S because it is a well order. So what that means is we want to have this definition, and we want it to have the property that the complexity assigned to one of these arguments of the recursive calls is always less than the complexity of the original input. So this means when we make recursive calls, we're applying them to arguments that have smaller complexity. The complexity always gets smaller and smaller and smaller, and this can't go on forever because we have a well order. So this is what ordinal recursion is. And if we look at ordinal recursion on the natural numbers, where the complexity that we're assigning to our inputs is a natural number, this is what people sometimes call natural number recursion. This is, if you're a programmer and you're going to define a function by recursion, the most likely way you're going to be doing it is by natural number recursion. Now, ordinal recursion is also called well-ordered recursion for obvious reasons. So that's ordinal recursion. Ordinal induction works as follows. Again, we have a well order here. And the ordinal induction principle for this well order is as follows. It says for all members x of S, if it's the case that we can prove that the property holds for y for any member of S that's less than x, then the property holds for x. So if we can prove that, we can prove that whenever the property holds for p of y, where y is less than x, it implies that it will hold for x. Then we know that it will hold for all x. So this is the ordinal induction principle for a well order, and it turns out the ordinal induction principle for the natural numbers is this principle. It says for all natural numbers, if we can show that whenever y is less than x, the property of y holds, well, we can show that if the property of y holds for all y less than x, then that always implies the property of x holds. Then that shows that the property of x holds for all x. Now this principle is called a number of things. It's called strong induction, complete induction, or course of values induction. And this induction principle for the natural numbers is, as you can see, different than the induction principle we saw earlier, which we called weak induction or just mathematical induction. That principle came from structural induction. This principle comes from ordinal induction. And ordinal induction is also called well-ordered induction. So the real reason we're interested in ordinal induction is because of this statement here. Ordinal induction is useful since complicated nested induction arguments can be expressed using the ordinal induction principle for gamma less than for some suitable ordinal. Now, there's two important points to mention here. So imagine we have some kind of very difficult proof that we're doing where we have induction, and within that induction we have another induction, and maybe within that induction we have another induction. So we have complicated nested induction arguments. These are very easy to get confused with. We can straighten things out quite a bit if we convert it to an ordinal induction principle. The thing is, we have to figure out the right ordinal to use. Now, I don't want to spend much time in ordinals because they are very confusing. Most graduate students find them very hard to understand. So as far as our course is concerned, it's completely optional. But I will spend a few slides and talk about them. And I'm not going to go in a lot of depth and try to clarify things because that will take a lot of time. It may not really work to clarify things. But at least I'll give you an overview. I'll give you the definitions. So an ordinal is a set. And it's a set such that if we look at the structure of that set with the membership relation, it is a well order. And if we take any member of our set gamma, that member will also be a subset of gamma. So this already starts seems a little strange. So ordinals are sets that have very simple but unexpected properties. Okay, so we get a proposition we could pretty easily show that if we have a member alpha of an ordinal, then alpha itself will be an ordinal. And if we have an ordinal that is a strict subset of another ordinal, then it will necessarily be the case that that ordinal is a member of that other ordinal. Alpha is a member of beta. So you see, ordinals have a lot of structure. So instead of writing this, A is a member of beta, we're going to write it as, I should say alpha is a member of beta. We're going to write alpha is less than beta. Now, if we are going to look at the ordinals, the first ordinal is the empty set, which represents 0. And then the n plus 1 ordinal is n union the set of n. So this is how we can represent the natural numbers of ordinals. And then if we look at the set of all these ordinals that represent natural numbers, this is omega. This is the first infinite ordinal. And the ordinal induction principle for omega less than is strong induction. So strong induction is the induction we just talked about for the natural numbers. So this is strong induction. And if we look at the ordinal induction principle for gamma less than, where gamma is something bigger than omega, that is what people often call transfinite induction. Okay, so if we look at all the ordinals, put them all together as a collection, it is itself a well order. And it sits between the natural numbers and the serial numbers. Remember, the serial numbers are in some sense the biggest ordered field. And we can also look at the ordinals. If we throw in 0, plus, and times, it has the structure of what's called a near semi-ring, is this algebraic structure. Now, what makes ordinals important is that for every well order S less than, there is some gamma, which is an ordinal, such that S less than and gamma less than are isomorphic. So they're essentially they have exactly the same structure. And we call gamma the order type of that well order. So ordinals are a way of characterizing well orders. So anything you could do with a well order, you could do with the corresponding well order that's associated with order type. Now I'm going to give and mention briefly some important examples of order types. So remember, these order types are types of well orders. So the first one is omega. Omega, as we mentioned, is the set composed of the ordinals that represent 0, 1, 2, 3, 4, and so forth. And it is the order type of the natural numbers with less than. If we have omega plus omega, that's the ordinals we have 0, 1, 2, 3, and so forth. Then we have omega plus 0, omega plus 1, omega plus 2, omega plus 3, and so forth. This is the order type of S less than, where we have the rational numbers like this. We have 0, 1/2, 2/3, 3/4, all of those. And then after those, we have 1, 1 1/2, 1 2/3, 1 3/4, and all of those. So that's the order type omega plus omega. The order type omega times omega is the union of all the ordinals. Remember, ordinals are sets, so we can union them up. It's the union of all the ordinals, omega times 1, omega times 0, omega times 1, omega times 2, omega times 3, and so forth. And this is the order type of pairs of natural numbers ordered lexicographically. The order type represented by omega to the omega, which will be the union of omega to the 0, omega to the 1, omega to the 2, omega 3, is the order type of S less than, where S is the set of base omega numerals. So if you think of a numeral in base 10, could have something like 384, where this would be the first position, second, and third. So in base omega numerals, we could have something like 312, 6100, 23. And this is the first position, second position, third position. And so omega to the omega is the order type of these base omega numerals. And finally we have epsilon 0. It's the union of 1, omega, omega to the omega, omega to the omega to the omega, omega to the omega to omega 4 times, and so forth. And it is the order type of S less than, where S is a set of all finite rooted trees. So rooted trees are trees that are finite, where we start with a root. We can have any number of branches, and then those can have any number of branches. And the order is a pretty obvious kind of lexicographical order. Now, something very interesting about epsilon 0 is epsilon 0 equals omega to the epsilon 0. Okay, so that is the end of this section on ordinal recursion and induction. And we'll begin next time with a little discussion about weak induction versus strong induction. Okay, thank you very much.